Let's take a charge at one place, Q. If another charge placed near to it, say that is Q naught, this Q naught will experience a force due to charge Q. Now, around this Q there is always a boundary that can be of any shape. If the charge is in the boundary, is within the boundary, it will exert a force due to Q. If it is out of that boundary, it is not affected by the charge Q. So the area around charge Q, in which if any other charge is placed, that experiences the force due to Q, and this area is called its electric field. This electric field is defined for charge Q, which is already present at that place, and Q naught, if it is brought in that boundary, it experiences force due to Q. Now, electric field is different at different points inside the electric field. If Q charge is a positive charge, then when we come closer to positive charge, the force on charge becomes more and more. That's why magnitude of electric field is more when we come closer to the charge. So magnitude of electric field at any point is called electric field intensity. This is called electric field intensity, denoted by E. E is a vector quantity, and intensity is defined as force experienced by unit charge. That means if a unit charge is brought from any point to a point inside the electric field, whatever force it experiences at a point, that will be the magnitude of electric field. So, as the charge comes closer, force will increase. That is why electric field intensity will also increase at that point. Then E is given by F upon Q naught. Its unit will be Newton per Coulomb. As we are saying that electric field is vector quantity, so direction of electric field, that is given by the rule that if we have a positive charge placed at one point, and because of this charge at point P, we have to find direction of electric field, then it will always be away from the positive charge and along the line joining this point and charge. So this is positive charge, electric field at P will be away from this positive charge. If charge which is already present is negative, then at point P electric field will be towards negative charge. Electric field due to point charge. The expression for electric field, because it's a point charge, it is given by using Coulomb's law. There is a charge Q placed at one point. There is a point P at distance r from this charge Q, where we assume Q naught charge is placed. Because we are assuming it, we call it test charge. A charge which is assumed to be present at a position, this is called test charge. Now Q and Q naught will experience a force. That force is given by 1 upon 4 pi epsilon naught Q naught upon r square. Now electric field at this position P will be force experienced by unit charge, so F divided by Q naught. This will be 1 upon 4 pi epsilon naught Q upon r square. This is the electric field intensity, at point P due to charge Q. We can see in the expression that electric field does not depend upon the test charge which was kept at point P. It depends upon only that charge which is already present in that area. Electric field line. This is a concept which is used to interpret electric field on paper. Electric field lines are not the real curves. They are not visible around a charge, but we draw them on the paper according to the properties of charges, which are very useful in predicting the nature or the forces of the charges that they exert upon each other, and the nature of electric field which is present around a charge. So electric field line is a simple curve which basically starts from positive charge and ends up at negative charge. If there is a positive charge and negative charge, it will start from positive charge, will move to the negative charge like this. So we can say that electric field line is a curve that starts from positive charge, ends up at negative charge, and at any point on this field line, if we draw a tangent, that gives the direction of electric field at that point. So the shape of curve is such that at all the positions, all the points on the curve, tangents drawn gives direction of electric field at that point. What properties are exhibited by electric field lines? First thing, they are continuous curves. Start from positive charge and then end up at negative charge, but between them they are continuous. Second property is that the field line shows the motion of positive charge. This gives the direction of motion of positive charge. Third property is, if there is no charge in a region, suppose in this portion there is no charge, then all the electric field lines will keep moving continuously without break, because break comes only when any positive or negative charge comes in between. This will move without break. Two electric field lines never intersect each other. They always move apart from each other, because if they intersect, suppose these two electric field lines, they intersect, there will be a point of intersection, and at point of intersection we can draw two tangents which will give us two directions of electric field at the same point, which is not possible. So electric field lines will never intersect each other. Fifth property, electric field lines do not form closed loops, because they go from positive charge to negative charge, but they don't come back from negative to positive. This is not possible. A uniform electric field is represented by parallel and straight lines. If in a place we show electric field lines like this is a uniform electric field. And if field lines are not uniform, then the place where they are dense, here electric field is more, and where the gap is more, electric field is less. This is a strong electric field and this is a weak electric field. We can draw electric field lines of single positive charge and single negative charge. if we have a point charge, positive charge, then electric field lines from this positive charge move radially outward along the radius of a sphere. They all move out like this. If there is a negative point charge, they all will be radially inward. They will be along radius of the sphere but inward. Electric field lines for two positive charges, if two charges are same, then they do not go towards each other. The lines are going away from the positive charge, and here the lines which were going otherwise to this side, they start deviating from this positive charge and they go outside, and here also they deviate to this side. In electrostatics, we have a term electric dipole. Electric dipole is a system, we can say, system of two equal and opposite charges. If we have plus Q charge and minus Q charge, and they are kept at some distance from each other, they are fixed at some distance from each other, that system is called electric dipole. The distance between them is generally taken as 2a because this simplifies the calculations regarding electric dipole. So we take it 2a. This is called electric dipole. For electric dipole, we define electric dipole moment. This is denoted by small p, and dipole moment is equal to the product of charge and the distance between them. Magnitude of one charge and distance between both the charges. Electric dipole moment is a vector quantity. Its unit is coulomb meter, and because it is vector quantity, its direction is from negative charge to positive charge. It is always directed negative to positive charge. So if we draw electric field lines for dipole that become positive to negative, here they go from positive to negative charge and they all come like this. And from positive charge they move out. This way.